Hello, Physics 2212, Lab 3, Circuits. The purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel using multimeters to measure the actual values of conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. I will be making use of Circuit Construction Kit CCK online simulation. Our system is the circuit and our surroundings is everything else, and our initial conditions are the created layout of each circuit that is required. Preview of the results. I1 is equals to I2, which is equals to 0.02 ammeters, and RC is equals to 6.906 seconds. Background knowledge. I made use of different physics principles here. The node rule. Current flowing into a node must be equal to the current flowing out of it, resulting in conservation of charge. Loop rule. The sum of all the potential differences around a loop is zero, resulting in energy conservation. Ohm's law. Current through the conductor between 2 points is directly proportional to the voltage across those points. Assumptions I will be making is that the assumption I will be making in this lab is that the CCK simulator accurately displays how the circuits would perform in the real world. Experiment 1. First, let's predict the currents in I1 and I2 that will be measured by the 2 ammeters in the circuit below. R total is equals to R1 plus R2, which is equals to 147 ohms. Then there are two 1.5 volt batteries in series, so the total EMF of the circuit is 3 volts. Moreover, because the circuits and ammeters are in series, I1 is equals to I2. Therefore, I1, which is equals to I2, is equals to 0.02041 ammeters in the circuit. I then simulated the circuit in CCK, and lo and behold, the 2 ammeters also read the current was 0.02 ammeters. So the calculation and the simulation experiment produced similar results, and the predictions were right. Note that when inserted backwards, it still reads the same. Now we replace one of the ammeters with a voltmeter. The voltmeter reads 3 volts and the ammeter reads 0 volts. This is because the voltmeter has a very high resistance and there are no major voltage drops. Experiment 1 as well. I am now going to touch the voltmeter around every part of the circuit and measure the PD across these different components of the circuit. The measured differences add up to 0 volts. As you can see here, these are the different potential differences across each component in the circuit, and they all add up, and once you add them together, they all add up to 0 volts. When you attach the voltmeter, you alter the circuit. Why doesn't the value of the ammeter change? The voltmeter has very high resistance, so almost no current flows through, and that's why. Here is a graph displaying the gradient of the potential, as you can see there. Now we connected an ammeter in parallel to R100. The ammeter reading in both the ammeters is 0.06 ammeters. This is because ammeters have very low resistance, so the current will flow through it rather than the 100 ohm resistor, making the circuit's total current 0.06 ammeters. We can also calculate the resistances of each circuit element using V equals IR, and as you can see, the 47 ohm resistor has the 47 ohm resistor has all of these, and the resistance of the wire is 0 and the resistance of the ammeter is 0. We will now be investigating RC circuits for experiment 2. For this investigation, we will be making use of a 10 ohm bulb and a 20 ohm bulb, a 9 volt battery, and a 200 millifarad capacitor. When I connected the 10 ohm bulb, 9 volt battery, and 200 millifarad capacitor in series, the light in the bulb was bright at first but slowly dwindled. The 10 ohm took around 10 seconds to charge and around 10 seconds to discharge, and the 20 ohm bulb took around 12 seconds to charge and around 50 seconds to discharge, around those two. It was a bit hard to tell because of, it was physical, like I was measuring it myself. Now we simulate the circuit with a 30 ohm bulb. The other components are the same. We set the capacitor discharging and plot 20 seconds worth of voltage versus time data on a ln delta V over delta V naught versus time plot. We will use the plot to calculate RC. Using the slope, I calculated RC, where RC experimental is equals to 1 over minus 1 over slope, which is equals to around 6.906 seconds. This is pretty close to the calculated predicted value of 6 seconds that RC would have if it was calculated with the equation. While they share similarities, they are different because one is calculated predicted value and the other is closer to real life. Sources of error. Human error when using the stopwatch to calculate the recharge and discharge time, as I showed you, as I talked about before, how it might not be completely accurate because I'm the one who calculated the time. And also, another source of error is that this is a simulated circuit, so it may not fully and accurately represent the real-world version of this experiment. What if? What if you charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach a full charge? Would this prediction happen in real life? Explain. With no resistor, the model will predict our capacitor to charge instantly. In the real world, however, components have resistance, so it will still take some time. And there's no why question. So yeah, that's the only what if question. And yeah, thank you.